guys, this is Mrs. Clay, and we are going to have to do this very quickly because we only have 15 minutes to do this in video. So we're going to get started real quick. We're going to learn the names and formulas for complex salts. So pause it for a second, pull out these three things, and then get started. Okay. So complex salts. Up until this point in time, we've talked about simple salts, which have to do with a cation and an anion bonded together. Now, a cation is a metal, anion is a nonmetal, so these things come together and get simple salts. Well, complex salts are still having cations and anions in them, but there is another player in it, and that is called polyatomic ions. So take a minute, you might need to pause the video to write this down, but polyatomic ions are what's the difference between complex salts and simple salts. And these ions form ionic bonds with either a cation or an anion. So essentially what it's doing, it's replacing, depending on what situation it is, it could be maybe the cation bonded to a normal anion that we're used to, or it could be playing as the anion, the polyatomic ion, and bonding with the cation. And you'll see a couple examples of what I mean in a minute. But let's spread out this word a little bit more. Poly refers to many, atomic refers to atom, and then ion is an atom with a charge. So if we wanted to put it out in more layman terms, we would say that a polyatomic ion is essentially many atoms with a charge. And notice how we say with a charge, all these atoms together, they all have the same charge, they work towards the same charge. Now something unique about these as well is they bond together not with ionic bonds, but with covalent bonds. So what's essentially going on within a polyatomic ion, these many atoms are bonding together covalently, and then when they get a charge, they'll bond to either cations or anions and create ionic bonds. So you'll notice that for complex salts, you'll deal with covalent bonds and ionic bonds. Simple salts only deal with ionic bonds. Okay. So let me show you guys something real quick. This is an example of a polyatomic ion. I will show you a paper in a minute of how we can figure this out, but essentially for our class, we don't need to know the actual names, we do need to know the names, we just don't need to know how we got them. So I will show you though real quick, this is a Lewis dot structure. We drew some of these earlier in the year where we had notice sulfur is the S and oxygen's the O. These are two nonmetals, so they like to bond covalently. They're sharing electrons, and we actually indicate that by these bars right here. And I'll actually pull that up in a minute. But notice also another thing. Oxygen itself does not have a charge. Sulfur itself does not have a charge. The whole thing has a charge, and we can see it because it's in a bracket, and it's to the -2. So this whole thing has a -2 charge. Let's look at another example. We have sulfite over here. Notice very similar. They both have sulfurs, they both have oxygens, but sulfite has one less oxygen than sulfate. And that actually has to do with the name. If you have any desire to learn more, you can ask me because there is a way to figure out eights and ites and all these other things. But that helps us determine what the Lewis dot structure looks like. And so you'll see that this sulfur right here now is only bonded to 3 oxygens, so it's only sharing 3 electrons. Each one of these oxygens is sharing one of them, and we show that sharing interaction as this bar. Now these other circles right here, we're going to call them lone pairs. So let me pull up these two things. I've already hinted at these bonded electrons right here now that are bars. We're going to keep drawing them as bars from now on. But then you'll notice that these dots that we've been drawing already, we like to call them lone pairs, meaning that they are not bonded between two elements. They're just kind of there. So we call them lone pairs. Okay, so how did I come up with the name sulfate and sulfite? Well, if you click on the actual presentation, you can click on here and it's going to pull up. Let me show you what it looks like. It will look like this. So this paper you should have gotten in class. You'll need to print it off. It'll be useful for doing homeworks and whatnot. But you'll see that the front page has basically a table or a layout of polyatomic ions that we can see in the class. And it's actually categorized by what charge they have. So notice ammonium right here has a +1 charge. It's the only one that we'll deal with that has a +1 charge. Notice we have a lot of -1 charges over here, and we have a -2 column over here, 1 -3, that's phosphate, and then mercury over here with +2. So what you only have to do for polyatomic ions is you just need to know how to read this chart and then make compounds out of them. So if you were trying to find sulfate, like our example earlier, it has the name sulfate and then SO4 2-. So this is just, can you look it up or not? Now you'll also notice if we scroll down the next page, there's this other big table. We're not going to talk about it right now, but it's going to come up later. But let's focus on this. So this table, you'll notice that a lot of these do not end in the normal "ide" that we saw for simple salts. For example, we used to say sodium chloride, potassium phosphide. We have these things ending in "ides." Well, most of these ends in "ates" or "ites." Let's see, what else? Perchlorates, manganate, there's just all these "ates" and "ites for the most part. We're going to notice that this trend continues very similarly for all polyatomic ions. That's probably the one biggest indicator that we know it's a polyatomic ion, is because the name doesn't usually end in "ide." Now, there are 3 examples on that paper I just showed you. Take a minute to pause this video, pull it up, and try to identify what those 3 are that end in "ide" and are considered polyatomic ions. Okay, so you should have been able to see that there are 3, hydroxide, cyanide, and peroxide. These are all polyatomic ions, and this is where you need to be careful. These end in "ide, but they are not saying that they are simple salts. Hydroxide is OH. Cyanide is CN. Peroxide is O2. And so we have to make sure that we're keeping to look at our paper, making sure that we are actually labeling this appropriately. So just be careful about those 3. Okay. Other than that, these are treated pretty much just like any other ion, meaning that they are going to want to have the same amount of charges be balanced. What I mean is overall charge of 0 when writing the chemical formulas. So just like simple salts, we want to balance out those charges. Something that is different, though, that we didn't see beforehand was this idea of using parentheses in the formula. Let me show you what I mean real quick. We're going to get out of this. If you need more than one polyatomic ion, put it in parentheses. What I mean by this is polyatomic ions are groupings. If I'm dealing with sulfate, it has 1 S, 4 O's, and the whole thing has a -2 charge. That whole thing is a group. I can't pull the sulfurs away or the oxygens. It's just not going to work. That's not how these things are made. So why do we need parentheses? Let's say we wanted to react magnesium and sulfate. Actually, that's not going to work. Let's get rid of this. Let's do lithium. Nope, that's not going to work either. We're going to have to change our polyatomic ion. Sorry, guys. Magnesium, and let's do NO3. Take a second and try to find NO3 on the polyatomic ion sheet. Okay, so NO3. Oh, should have not said 3 out loud. It's confusing me. NO3 is actually has a -1 charge, and it's nitrate. So we're going to say NO3 -1. We want to interact these 2 together. If we take one of each, they obviously don't equal 0, so we're going to need to add more of something. We have too much positive right now, so let's add another negative thing. We have to add the whole entire group because we are dealing with the whole thing has a -1 charge. So now that we've added these up, +2 -1 -1 equals 0, we are going to see our formula say MgNO3 2. Anyone have a problem with that? I do. Let me show you where. This 3 and 2 right next to each other awfully look a lot like 32, which is saying that you have 32 oxygens. We'll count real quick. 3 from this nitrate, 3 from this nitrate. You should only have 6. So what you want to do, and this is why we need parentheses, we need to put parentheses around the entire thing to say that, like a math problem, 2 times whatever is in the parentheses, that's what we're going to multiply by 2, and now we see that we have 2 nitrates in our formula. Perfect. I am going fast, guys. Hopefully you are pausing throughout this. Okay, so More than one polyatomic ion, put in parentheses. If you only have one or only need one, don't use parentheses. It's redundant. Okay, perfect. So guys, I have a couple examples for you, and because I am low on time, I can't spend time on these too much. I am going to say, though, that calcium you can find on the periodic table. Sulfate, look at the ending. It ends in 8. Determine if that's going to be a, what's it called? A polyatomic ion or not. Now, notice nickel 3 hydroxide, for example. You have to find out the charge of nickel. It's written somewhere in here, hint, hint, nudge, nudge. And then hydroxide is one of the exceptions. It is a polyatomic ion. You're going to have to find out what it is and then combine these to do that. I'm going to skip through these real quick for sake of time. This is more practice going the other way around. You're given the formula. This is actually wrong. It should say K2Cr2O7. So this 7 should have been a 2. That's my bad. I still need to change it. But this is just going the other way around. I'm going to let you work on those by yourself some other time. But this is where I wanted to get at the end. Next time we are planning on doing a lab, and it has to do with putting salts in water, mixing them up, and sometimes we get different results. And all it has to do with this word called solubility. So let's write that down. Solubility is a measure of a compound's ability to dissolve in a liquid, generally water. And we're actually only going to work with water in this class. So, solubility, basically, if you put something in water, does it disappear? Does it stay there? That all depends on its solubility. So, I have this lovely pyramid that we are familiar with from term 1, where we talked about solutions just briefly, where you have a solute, the dissolvee, and the solvent, the dissolver. That's what we're going to be working with the next couple of days. So, there's a couple other words we need to know, and I know we're rushing through this really quickly, but this will all make more sense once we start doing the lab. If something dissolves in a liquid, it's soluble. But if it doesn't dissolve in the liquid, sometimes you want to talk about whatever solid didn't dissolve, and it's actually called a precipitate. So write down precipitate. It's when something doesn't dissolve, it just sits in there, and we want to talk about it. Now there's 2 other words, and these are going to be helpful for your homework assignment. Soluble means that it does dissolve, and insoluble means it doesn't dissolve, meaning that a precipitate has formed. So, for example, table salt, sodium chloride, whenever you put it in water, it does dissolve. We would call that soluble. Now, if by chance we took a different salt and put it in water and it didn't dissolve, we could say it's insoluble and it has a precipitate. So you'll get familiar with more of these trends later. Okay. Oh yes, let's identify the solvent in here. If the solvent is a dissolver, we're only going to work with one in this class, and that is water. So the solvent is water, and then that leaves our solute to be the salt. So we'll create a solution out of salt, water, and then we'll get different results next class. This thing I didn't get to for a lot of my classes, so here's for you if you read through this. This is just some practice. You'll notice it says flip over the paper containing polyatomic ions. That's the sheet that I showed you earlier that has a bunch of S's and I's. It has a key to the top of it which shows you what these things are doing. If it's soluble or partly soluble. On the homework that you'll be given, you'll need to be able to write the names and formulas of these things and then identify if they're soluble or insoluble. And it's as simple as looking up on the table and seeing where do the 2 meet. So you're going to find whatever positive thing is reacting with what negative thing. There should be a box that intersects those 2, and in that should be either an S or an I or some other number, and that's what you're going to put for your answer on if it's soluble or insoluble. So we'll just do this example real quick. Find potassium for me on that table. It should say K+. Then find hydroxide, which is OH-. At the point that those 2 intersect on the table, it should say S, which stands for soluble. So the answer for that would say soluble. We're going to click through these real quick. I just wanted to show you guys this real quick. People were getting confused about simple salts versus complex salts. You'll just notice that the wording gets a little bit more complicated and fancy. So you guys know this. We are doing a lab next time, And the quiz, it says next time, but what I really meant is it's online on Canvas and you can do it at home. Thanks, guys.